Today we're going to be talking about milestone 1 and how to get going on it. So let me give you a quick overview of milestone 1. Well, basically you're going to be interacting with some APIs that we wrote for you that are in a library. Library is just a collection of .o files, and large programs usually are not just one executable. They're usually a bunch of libraries and a smaller executable program that calls them. So in a couple of lectures, we'll get into why did we organize your project this way, but it's better for testing and for ease of building your project to divide up a large program into libraries like this. But you can just think of this as this is a piece of an executable program. Okay, so we've written some code for you that we call the Streets Database API, and that's put together into a library that you can talk to. You can't modify it, we wrote it, you can only call it. You are going to be writing almost all your code in another library that we call the Street Map library. And the Street Map library can be called in two ways. It can be called by a test executable, and again we'll go over in lecture what does this mean. But this is a more scalable, more disciplined way to test a large program, is you actually have a test program that talks directly to your functions. So this is what ECE 297 exercise is doing. It's a test executable that is calling into these functions that you're writing in your Street Map library to make sure they do the right thing. Later in the project, you're also going to be using a main executable, and the main executable is essentially the start point for the program that an end user would use when they want to interact with your map. Both of these executables are going to call a load map function, and your Street Map library is going to interpret that as I should load whatever data I need to be able to answer queries, do useful things. And when they're done, they're going to call close map to tell you, okay, if you allocated any data, set up things, you should go destroy all that right now. And in between that load map and that close map call, we're going to make queries. So queries are, we're going to define a bunch of functions that answer interesting questions for our test executable, and they are likely to be useful to you when you go on to later milestones as you're writing your main program. So you're going to get some mileage out of most of these routines. Those questions are going to be about the city that is currently loaded. So you can load a variety of city maps, and you will do that when we make this load map call. And we're going to ask questions. How many intersections are there? What's the name of the first intersection? That kind of thing. In order to answer those questions, you will have to make calls in turn to the library we gave you. So we document what are all the capabilities of that library that you can use. Okay. So everything in dashed lines here, you have to write, and everything in solid lines is already written. Okay, so what are you going to do to get started? So you need to read the handout. So there are many students that go and read the handout. That's the right approach. Some students basically think maybe I can just skip reading the handout and I'll just try to figure out what I'm supposed to do by looking at Piazza and so on. It's not a very efficient approach. The handout gives a bunch of background information and more detailed specifications, so you really want to read it. You're going to need to have at least one global variable, and I'm going to talk about why you need that later, but basically this load map function is going to have to store some data, and the way for these queries, which come later, to get access to that data is there has to be at least one global variable to kind of allow these things to connect. And you're going to make use of the container classes that we talked about for the first two tutorials. So in STL, there are a whole bunch of container classes: vector, list, map, unordered map, multi-map. Those allow you to rapidly build data structures of different types. So part of milestone 1 is based on what you're trying to do, the queries you're trying to answer and how quickly you need to answer them, you choose, well, what kind of container should I use to organize this data? Which is one of the learning goals of milestone 1 as well. Gaining experience with using the STL, gaining experience in choosing the appropriate data structure for various purposes, which is a very important skill for your career. Okay, so diving a little deeper, how do we represent these city maps? So what's the underlying data that you're going to be working with? So the way we represent a city map is we have intersections, which, as I talked about in lectures, we can think of these as nodes in a graph. And each intersection has an ID. So this might be intersection number 317, and that would identify it. And then the other really key data structure in the APIs you're talking to are street segments. And a street segment is a piece of a street that goes between two intersections. So basically a piece of a street that is as long as a city block, and every one of those also has an ID. So in this case, that street segment might have an ID of 522. So what are you given to start this milestone? We give you a little bit of skeleton code. So this skeleton code is in a file. You're going to write all of your code for this milestone in libstreetmap/source. So those are source files that will turn into this streets library. And you can write as many source files as you want in this directory. You can name them anything you want. The makefile we provided you with will compile them all and put them in the library. We've given you one skeleton file to get you going, m1.cpp, and I'm showing you a sort of slightly shorter version of what's in that skeleton file. So this basically includes m1.h. That's a header file that we wrote, and that header file, I'm going to show you pieces of it in a minute. It basically defines what are the functions that you have to write. It also includes Streets Database API, which is the main API that you're going to call. So we've written all the functions in Streets Database API. You only need to know how to call them, which means you only need to look at the header file. And you're going to call those functions in order to answer questions. So part of this milestone is also getting you familiar with how does this API that we wrote work, how do you use it. And this is what, as I said, is in m1.cpp. One of the functions you have to implement is called loadmap. Loadmap is called before any other functions in your library will be called. And basically we pass you a string, which is the name of some map. So it might be Toronto.streets.bin. We name all of these maps with streets.bin. So if that was the name, you should basically call, this is all in the milestone 1 handout, but you basically should call our functions to load the Streets Database API call, and you might want to load some of your own data structures because maybe you want to store some things that'll make later calls faster. And as long as everything went well, you'll return true. If anything went wrong, you weren't able to successfully load the map, then you would return false, saying you failed. And then you also are going to implement a close map function that basically deallocates any memory that you created. So if you've loaded data by calling one of our functions, you're going to call our close function to get rid of it. If you've made your own data structures, like you created some vectors or maps and so on, you would clear them out here. So getting rid of all the memory. Okay, so how do you attack M1? So I just showed you the skeleton file that you're given. You want to iterate rapidly when you're developing software. So you are going to, as the handout says, to get going, you're going to run the command ECE 297 init 1. Okay, so that's going to initialize milestone 1. Every team member should run that. What it does is it sets up a shared repository in Git for each of you. So you've got a remote repo, you're all connected to it. You'll get a few files, like this skeleton file, will be in your local repo, in your working directories. So you've got a few files to start working with, and you're all connected through Git. So next thing you've done after you've run that command is you should compile to see if the program builds. And then you're going to be testing over and over again. Remember, we have this text executable, which is called ECE 297 exercise, and it always takes a milestone number. So we're going to call it with argument 1 now. That's going to run all of the public tests, and there are a lot of them, on your functions. So it's going to tell you how you're doing. So let's say you do that. What happens? Well, you never even get to this stage. What's going to happen initially is you're going to get a whole bunch of undefined reference errors. Okay, so this says in this particular function, and this is a particular function that you can read. This is a public directory. You can read the path here. It's a function that we wrote. It's in a file that says milestone 1 functionality tests for intersections for Toronto, and they're public, so you can look at them. On line 185 of that file, which we wrote, there's an undefined reference to find street segment length, which is a function that should take an integer as its input. And you get a whole bunch more of these. So other lines also have undefined references to this function, and then basically the build fails. Okay, the basic. So what happened? What's going on here? Why did I get a build failure? Does anybody know how to interpret these messages? Okay, so if you know, just unmute yourself and say, or type it in the chat. This is a good test to see if people are following me at all.
I think the first one is because you didn't even write the function find street segment length, and it's probably like trying to use it.
Yeah, that's exactly
Didn't define.
Yeah, so this undefined reference error says you told me this function exists. Like you're actually trying to use this function, and you're trying to use it on this line of this file, but I can't find this. I can't find the body of this function, the definition of it anywhere. So I can't proceed. This error is coming from what's called the linker. Okay, so compilation actually is first take all of these .cpp files and compile them into .o files, and then take all those .o files and do what's called linking them together, like seeing that all the function calls match up to some function. And that's done by LD, the linker, and the linker saying, I failed because you asked to call this function and I don't see it anywhere in any of the object files. And the reason that happened is exactly what we said. No one's written it, right? This is one of the functions you're supposed to write. You haven't written it yet. So the skeleton project we give you won't actually compile, which means you can't even run any tests. So our first step is we need to make this compile. What's the fastest way we can make this compile? Let's see if I can, yeah. So I guess I'll give you a little more context to help you. If you go look at m1.h, m1.h is the specification of what you have to do. So it is a bunch of different functions that you have to write, and it just tells you what the functions do and how they'll be called. Now, obviously, you have to go write the body. So this find street segment length that just failed, it says it takes one argument. It says it's a street segment index. Street segment index is type def to int. So from the compiler's point of view, this is just an int. That's why it said I couldn't find this function taking an int. We've done this type def to just make the API that you're writing a little more self-documenting. You can tell that while this takes an integer, that integer should be the index of a street segment. But basically, this is just a nickname for int. And the comments in this header file tell you, what should happen. So this function should return the length of that street segment, whichever one we passed in. We passed in a certain ID, like 500. Tell me the length of that street segment in meters. And the speed requirement says it has to be fairly fast. So we're gonna speed test it as well. And there are about 14 functions you have to write. So you see every one of them, we define what the function is, and there's a comment above it saying how it should work. Okay. And I see an answer from Rohan of, okay, how do we make this compile quickly? So I've got maybe 14 functions in here. They're all missing. It wouldn't be a good practice to try to actually write the real function for all 14 of them and not be able to compile until I wrote the 14th one, because I can't test. I can't tell if I'm getting closer. So that's not a good idea. So yeah, we should do what's called stubbing out these functions, which means just return some legal value. Don't worry about it being correct at all. In fact, it won't be correct, but it will compile. And this is a very common technique when you're programming. You know that you need to have some functions. Your teammates are relying on you having these functions. You don't have them yet. You stub them out so at least will compile. They can't really use them, but they can still compile again. Okay, so let's see. I see a question. Is this similar? Is there something similar to pass in Python? I mean, the equivalent of pass in Python just means I didn't put anything here. In C++, the equivalent of pass is you just leave it blank, right? You just don't put anything there. So yeah, what we're going to do is we're going to create empty implementations of those functions to m1.h. This is such a common thing to do that there's a name for it. It's called stubbing out the routines or writing stub implementations. So all we have to do is make sure we return the right kind of thing, and we do not worry about it actually being the right data at all. In fact, we know it won't be the right data. So let's see. Once we've stubbed out the routine, then we compile. We do that for all 14 routines. So we make very simple implementations for each one that basically just return some object of the right type. We don't really care what is in it. After we do that, it will compile. So now we can get to this step. We run ECE 297 exercise, and again, it takes the milestone, so milestone 1. And we fail all the tests. So you see that there's a test summary, and the tests are divided into kind of categories called test suites, and we basically failed almost everything. We actually passed a few of the Valgrind tests. Valgrind's mostly testing for memory corruption, so we didn't actually do anything, so we didn't actually corrupt memory, so we passed most of those tests. But everything that's trying to do something useful, we failed it all. Okay, so your goal for M1 is to improve this situation. Ideally, you fail none of the tests. If you fail some of the tests are harder than others. You get part marks, right? So this is not a lab. It's intended to be a little bigger than a lab, which means some of the tests are harder. Don't panic if you don't pass all the tests. It's going to be common for students to pass only some of them. So your goal is to pass them all. It's not the end of the world if you in the end are not able to pass them all. Okay? Okay, so let's look at how we do this. So I'm going to go into one of these functions. And that one function that we're going to look at is find street segments of intersection. And this is really one of the functions you have to implement. So by the end of this tutorial, you should know exactly how to write this one. It should be done really fast. Okay, so this function, we can tell what it's supposed to do and what data it takes as input and output from the header file. So it takes an intersection ID, which is just an integer, but we're going to use this type def, this fancier name of intersection index, to tell us what kind of integer it should be. It should be an ID of an intersection. And it's going to return a vector, and the vector is also indices, and they should be the indices or IDs of street segments. So for an intersection, we're going to pass some number of intersection, maybe it's 500, and we're going to return the IDs of all the street segments that go there. So maybe there are 4 different street segments, and maybe the first one has ID 30, the next one has ID 40, 55, and so on. Okay, so initially, this is the code I have. This is not given to you, but this is what I've written. Okay, from the header file, I know this is how the function is supposed to be called, so I write that. I've basically declared a vector of the right type, so street segment indices, called it SSIDs, and I return that SSIDs. So will this compile? Is this actually enough to make my function compile? Yeah, so it's going to compile. So this actually would be what you do to stub out a routine. I wrote the right header for my function, I created an object of the right type, and I returned it. I mean, it's going to be an empty vector, so it's not the right answer, but the compiler will be happy with this, so that's actually all it takes to stub out a routine. Now I want to go beyond that and actually start writing what is this thing really supposed to do. So our only input is an intersection ID number. So pretty clearly we need some other data that was not passed into this routine to answer the question. And that other data is in Streets Database API. The API we gave you can answer questions. So let's take a look at what's inside that API. There are a few things. So first, there are streets. I said that the kind of most important stuff we're giving you in a city map are the intersections and the street segments. So a street segment is, again, the piece of a street that goes between 2 intersections. So it's like a city block. And there's a data structure called street segment info that for any street segment allows you to look at some data on it. Important pieces of data for you right now are from and to. So these are the IDs of the two intersections that connect it. So there's a from intersection, there's a to intersection. There's a Boolean that says if it's one way. So if one way is true, then it means that you can only go that way. You can leave from and go towards to. If one way was false, then you can go both ways. Then you can think of it as having an arrow on both ends. And it's got some other useful information. If it's curved, it'll tell you about that. It'll tell you its speed limit. It'll tell you the ID of the street that it's part of, and so on. But what we're mostly interested in right now is just this part. We're interested in street segments and in intersections. Other functions in Streets Database API that are useful to us is we can take an intersection ID. So again, maybe this is number 500, and we can call this function get num intersection street segment. So what that tells us is, again, let's say I passed in the number 500 as my intersection ID. It's going to tell me how many street segments intersect that or touch it. So in the little picture I drew, this would return the number 4 because there are 4 street segments. Now, I also want to get the IDs of those street segments. I want to know which ones. And that's where I can use this second function. This second function, we pass in the intersection index. So again, maybe that's, let's say 500 again. So same intersection ID. And we can now ask, tell me the street segment index of the first thing that touches this. So we can say segment number 0. So maybe that returns this one. And maybe that is an index of 300. And then we could also ask, okay, let's make another call to this, but let's ask for segment number 1. And maybe that turns out to be this street segment, and maybe that has an index of 412, and so on. So by calling this function 4 times with different segment number values, 0, 1, 2, 3, we can find what the IDs of all 4 of these street segments are. And for any street segment, we can pass its ID, so maybe 300, into this function get street segment info, and it's going to return this data structure so that I can look inside of it and see all of this more detailed information about that street segment. Okay? You're not going to remember all the details of what I just told you. This is kind of getting you used to the API. A big part of milestone 1 is by using this Streets Database API, you become more familiar with it. So that's part of the purpose of the milestone. Okay, there is a naming convention that we're using in these functions. So this function get num intersection street segment. So that's the one that I told you, for example, would return 4 for the case I showed you. So how many street segments interact with this particular intersection? Let's break down its name. So it starts with get, which by our convention in this API means it's a lookup. So it's going to get you some data. And our lookups are fast. They're usually order 1. Num, okay, so that's just saying it's a number. And basically say intersections. So that's, what am I asking for? I'm asking for the number of intersections. Well, I'm asking for a number. And I'm asking for it about intersections. Okay, so I want to know a number and it's related to intersections. Which number? I want to know the number of street segments. Okay, so I'm querying the intersections. Tell me how many street segments you have. So this thing I'm querying, this entity, often matches the argument of what I'm passing in. You don't have to memorize this. Basically, you read this in the .h file that we give you. There is a Streets Database API.h file. It's heavily commented, and we even include it in the Milestone 1 handout, so you can read it there if you prefer. But this helps you make sense of the names, so they don't seem so random. Let's see, there's a question, where can we see the API.h file? So it's in the Milestone 1 handout, so you can read it there. In your, if you're using NetBeans or Eclipse or another IDE, you will see, if you just include Streets Database API.h in some .cpp file, you can then browse to it. So you can just click on that include line and say go there, and it'll actually open up the header file and you can see it. The milestone 1 handout again tells you this, but the header file is in a public directory called CAD2 ECE 297S / public / include. Okay, and I think it's underneath there. I think it's under there under streets database / streets database API.h. So you can go to that path and you can look at any files in there, and that header file's there. You don't have to memorize this path though, because in your IDE, again, you can just click on the include file name and say go there, and it'll open it up for you. So that's how most people do it. Okay, so that's the function. I've shown you a few of the functions that you need to query from Streets Database API in order to implement this first M1 function. This just basically draws what I showed you before. So I've got intersection. Let's say this intersection is intersection ID 232. If I say get num intersection street segment for 232, it's going to return 3. Okay, so basically we're looking at this intersection here. So 3 street segments intersect it. So when we ask how many street segments intersect you with this API call, we'll get 3. And then we want to know what are the IDs of those 3 street segments. So we're going to make this other API call, get intersection. So from the intersection, get me the street segment. I'm asking about intersection number 232, and I want the 0th or the first street segment that touches it. So maybe that's 311. That's the ID of that. Then I ask, well, okay, give me the next one, right? The number 1 street segment. So that gives me maybe 321 is the ID of that. And then give me number 2, the last one, which is 352. Okay. There's no ordering convention here or anything. Basically, if I have 3 street segments that impinge on this intersection, which I get by asking this first API, then I know that I can ask about them by saying, give me the 0th, the 1st, and the 2nd, and I'll get the IDs. And I shouldn't assume anything about the relative order of those IDs. They're just integer IDs. Don't assume anything else about them. Okay. And then if I need to know, this is an ID 311. If I want to know more about street segment number 311, I call get street segment info with that ID, and that gives me that structure that I showed you earlier, that I can look at its member data in order to say, is this one way, what's the from intersection, what's the to intersection, and so on. Okay, so if there are any questions, just jump in the chat and let me know. Okay, just a few words about these types that I'm passing in. So this get num intersection street segment, I'm passing in an intersection ID because the question's about an intersection. And notice the type is intersection index. And sometimes I also have, you see some of these other API calls. This one, for example, I'm asking questions about street segments, so I pass in a street segment index. Something to be aware of is that intersection index, street segment index, any other indices that we define in these files, they're all type defs, which basically means an alias to integer. So from the compiler's point of view, all of these things are integer. It's the same as if you wrote integer. What it means is if you actually had a variable that was of type street segment index and you passed it in here instead of an intersection index, the compiler can't tell. So you're not going to get a compiler error. So be careful that you know what kind of index you have. Give your variables meaningful names, so it's less likely you mix them up, because they are all really integers. It's up to you when you're programming to keep track of which one's a street segment index, which one is a intersection index. And basically these type defs are just to kind of help you make it a little more self-documenting in your code, but the compiler won't flag errors if you mix them up. Okay, so we're going to try to implement this function. So we're writing this find street segment of intersection function, and so it takes the ID of an intersection, returns a vector of the IDs of the street segments that impinge on it. And I just showed you an example of what it should do. So I'm giving you the stubbed out version. We've allocated a vector. It's a default constructor, so it's going to be an empty vector, and we're going to return that vector. You need to write a function, or you need to write the body of this function that actually loads it with something useful. And you are probably going to need one or more of these function calls that we've just gone through. So I'm going to put you, everyone in breakout rooms now, and let's see, give you about 4 minutes to try to write this. So we'll see how you do. And then we'll come back here and look at what you got. Okay, welcome back everybody. How many of you were able to, was that enough time? Just type yes, you got it done, or no, didn't get it done. Okay, so there's one yes, that's good. See if anyone else got it done. Okay, so I got a few saying yes, that's great. So if you've got an answer, and yeah, you're right, Suleiman's saying we don't need get street segment info, and you're right. For this API call, you don't actually have to access get street segment info. If anybody's got a version they want to share, type it, just paste it in the chat and take a look at it, see how it looks. Okay, so let's take a look at this one. Let's see. Okay, so you've got okay, so you've basically created an empty vector, then you get the intersection count by making the first API call. Then you walk through every one, basically you loop through, asking one by one for the street segments and pushing them in the back of the vector. Yeah, that looks good. So that looks perfect. And that actually looks very close to what I wrote. Okay, so you can see this, yeah, you see another version of this basically in the chat. So that's kind of perfect. So got an index variable. It's going to go from 0 to the number of street segments that connect to this intersection. For every one of them, I say, okay, give me the street segment ID for this intersection and for that loop variable, so 0, 1, 2, 3, whatever, and just push it back into the vector. And once I'm done, I can return that vector. So yeah, so it looks good. If we run the tests after we've written this, we run ECE 297 exercise for milestone 1 again. When you run ECE 297 exercise, by the way, all the scripts we write for this course take -h as an argument, which will make them print help about how do you use them. So if you don't put any arguments for 297 exercise, it runs all the tests for that milestone. So that's often what you want. But in this case, to save some time, I'm telling it, I only want you to run a certain tester. I want you to look in your test suite and run any tests that have the word intersection in them. This basically means any characters you want, any characters you want. The quotes mean protect this from the shell doing anything weird. But it has to have the word intersection in it. So if we do this, we're actually going to see only 2 test suites run. The functionality one for intersections and the performance one for intersections. And we see that our functionality one passed now. 0, 4 tests failed. Our performance still failed. And in fact, it says it timed out. So it failed by a lot. So yeah, you can look at the options for 297 exercise. You can have it tell you the names of all the tests with one option called list testers, and you can tell it to run specific tests just because you want things to go faster. Let's see, is there a way to say a question, is there a way to ask the tester to run all functions that don't contain a certain word? There should be. I haven't done that, but basically this is called a regular expression. So you can write regular expressions that mean everything that doesn't match something. So it is possible to write that, but I haven't written it. Okay, so passed functionality, which is good, but we failed performance. So let's go into m1.h and look at it to see if it gives us any hints of what does this mean. Well, you'll see that find street segment of intersection has a speed requirement of high. Okay, and you look up earlier in the header file, it tells you what that means. There are 3 different kinds of speed requirements. Let's go start from the bottom. So none means there's no speed requirement. As long as it gets the right answer, it's okay. We time out the test after 5 minutes, so if it took longer than 5 minutes, it'll get killed, but other than that, it's okay. Moderate means it should be reasonably fast, We are going to speed test it, but you shouldn't have to store any data. If you just make the appropriate calls to our streets database API functions, you should be fast enough. And high is tougher. High is basically as fast as you can make it. So we do not expect that you can make it fast enough just by calling streets database API calls every single time. Instead, we expect that you have to actually create some of your own data structures, and you can do that in load map, so that you can rapidly return the data instead of actually kind of building it up on demand using streets database API calls. I'll talk about this some in lecture, but basically when you create these data structures, what we expect is that you use a data structure with the lowest computational complexity for what you're trying to do. So choose an appropriate data structure and you'll pass the test without problems. Choose an inappropriate data structure and you're going to fail by usually a lot. Okay, so let's look at the complexity of the function that we just wrote. So, well, what do you think the complexity is? All of the functions, these get functions that we give you are written to be fast. So they are typically order 1. So you never actually called this one, but you called these two. And you can assume they're both order 1. What's the complexity of the overall function? Yeah, so I guess maybe I need to give you another variable. N is, we're going to use N for something that's kind of big, like number of intersections, number of street segments in a city, because that can be big. That can be hundreds of thousands. For a city like Tokyo, it can even be millions. There is a loop here. Let's call the number of times we go through that loop K. K is the number of street segments that are connected to some intersection, because that's usually not that big a number. You could have 4 street segments at an intersection. You might even have 6 or maybe 8 for some really complicated intersection. It's going to be pretty hard to make an intersection with 10,000 or 100,000 streets coming at it. Somebody should not have gotten their civil engineering degree if they managed to do that. Yeah, so if we define this new variable k, which means it's not 1, but it's kind of bounded, it's not too big, then this is order k. We have a loop that we go through k times, once per street segment, and inside that loop, this is an order 1 operation, this is an order 1 operation, so the whole thing is order k. So that's not bad, actually. It's order k, and k is not very big. It's going to average about 4. So, maybe this will pass the speed test, but I just ran it and it didn't. So I still need to be faster, even though this isn't too bad. So what could I do? How can I be faster? So any ideas? Speed it up by only calling the getNum once. Yeah, that's actually a good idea. Okay, so we put this getNum could be called multiple times. It actually depends on how well the compiler optimizes it. When you're in debug mode, this is for sure going to get called once every time through the loop, which is a bit wasteful. When you turn on optimization, the compiler will try to figure out if it's safe to call this once and store the value. So it may call it just once, but it's also possible that it does call it multiple times. So it is actually a little bit safer to basically do something like this. So int, num seg equals, and then we call this function. And then inside here, we use that variable. Because now there's no guesswork. For sure, it's going to get called once. The compiler doesn't have to do any work to try to figure out if that's safe. So that is a good idea. Any other ideas for how we can speed this up? So the other idea is you can't speed up by rewriting this code. All right, you have to go further. You have to make a data structure. So, and there's a big hint in m1.cpp. So you're given a skeleton that has this load map function, and it says load your map related data structures here. So you can load anything you want. So yeah, and I see that's what Sage is saying. Load everything in load map and then just grab them. And that's exactly the approach that we're going to use to make this faster. Okay, so we need to choose, well, what data structure? Right? STL actually lets us make any data structure, well, a wide variety of data structures very quickly. So that's great, but now we need to pick from the menu. What are we going to do? And I see some ideas already, so let's just go through the thought process of this. So we look at our input. So our input to this function is an intersection ID, which is really an integer. So that's what's coming in. And a nice thing about this intersection is that its range is from 0 to get num intersections minus 1. get num intersections minus 1, again, for Toronto is about 150,000. So we have kind of a dense ID space. We go from 0, there will be an entry 1 and entry 2, up to some number, say 150,000, and there are no gaps. Okay, that's the ID space that we're presenting to you. We've organized the data so that that happens. Your output is a collection of street segment IDs, right? So you pass back a vector of street segment IDs, which are really integers. Okay, so we need to think of, well, what can we use for this? And I see various ideas: hash map, vector, unordered multimap, all reasonable ideas. Let's look through our whole menu. Okay, so we got vectors, we got lists, we got map, we got unordered map. So a vector can take an integer as input. It's like the index. The output can be anything, because we can store anything we want in a vector because it's templated. And this is the way we would use a vector. So a vector would work. A list is a bit inconvenient. Its input is actually not an integer, it's an iterator. Okay, we could write code, and there are STL algorithms. They're basically templated functions. There's a find function that we could call, which will go find things in a list and return an iterator. So we could use a list, but it looks a bit inconvenient. It could return the right type. A map, well, the key can be anything, so we can make the key an integer, that's fine. The value can be anything, so we can return a vector, that's fine. And an unordered map is similar, right? So it's just, this is a hash table, this is a binary search tree, but both of them take any key, any value, so they're going to work fine too. So list looks a little inconvenient, because it doesn't actually take an integer as an input. We could make it work, but it doesn't look like the best fit. Okay, but we could use any of them, with list looking a bit questionable. What can they contain? All of them can contain anything, so they could all return a vector, that's fine. And now, what is the complexity of accessing them? Okay, so a vector's fast, right? We have that square bracket operator, it's order 1. A list is slow. If we actually called the STL find function on a list, and we said, look for a list entry that has this integer in it, it has to search the whole list, it's order n. So list is a really bad choice. Okay, strike that off, that's terrible. A map, we could search, we could do find with an integer ID, it's log n, because it's a binary search tree. Unordered map, similar, but it's a hash table, it's order 1. Okay, so from these, we're going to pick the lowest complexity. So we're going to say vector and unordered map are our candidates. Map isn't terrible, list is terrible. Okay, so what would you pick? I saw some people saying vector, some people saying unordered map or unordered multimap. We don't need a multimap because we will never have duplicate intersections. Every intersection is guaranteed to have a unique ID. So map is fine. We on purpose don't need multimap. So we're down to vector versus unordered map. Type in the chat if you prefer one versus the other. Just say vector or multimap or unordered map. So Simon likes vector because it seems simpler, and I think that's, yeah, and we see some other people saying vectors. People like vectors, and that's a good intuition. Okay, so both of these are order 1. So you could say, well, it doesn't matter. But remember, order 1, there's still a constant in front of that, and the constants aren't the same. So for a vector, you're going to find this as you study how computers work in more detail in ECE 243. A vector is like an array. To get an element, you just have to add basically the index to the start of the array pointer and go look up the value from that memory location. Okay, so there's one addition and there's one load instruction. That's pretty fast. An unordered map involves a call to a hash function. So it even though you're passing in an integer that actually would be a pretty good index, an unordered map is going to hash that. So that function kind of scrambles the bits, produces a new index. And then with that new index, it's actually going to do something fairly similar to a vector. It's going to go compute, okay, where should I be looking up in the hash table, and let's go do a memory access. This hash function took time, okay? So we don't, so this is better, okay? An unordered map would be okay, but it's going to be slower than a vector by a factor of, probably 3 or 4 times slower. It depends on exactly what the hash function is and so on, but a vector is going to be noticeably faster, and it works fine in this case, so use a vector. Okay? So I'm going to end in a couple minutes, but maybe, and this will be recorded. So if you have to go, go and you can look at the recording. So when do you need a hash function? So arrays and vectors are indexed using a number, and if that index has certain special properties, it starts at 0 and it ends at some value, which is basically size minus 1. That exactly matches how you access an array or a vector. And notice the IDs we've given you, that's how they work. So that's really useful. But you can have cases where your input isn't an index like that. So let's say that we actually wanted to look things up by name. So we have strings. You can't use strings as an index into an array or a vector. So that's where a hash table is very good, because you can use the string as a key. You also might sometimes have to look up things by a really big number that doesn't start at 0. So for example, we have OSM IDs, which we haven't talked about in this walkthrough, but that's one of the functions you have to write in milestone 1, uses OSM IDs. OSM IDs are really big, 64-bit integers, so it's a huge number, 10 to the 19th different values, most of which never occur. So that is not a nice index that starts at 0 and goes to size minus 1. You cannot make a vector or an array that big, so now a hash map or an unordered map becomes a good choice. Okay? And let's see. What would you prefer? Do you want me to end here or go on for 2 or 3 minutes? I can cover the rest of this next tutorial. First person to vote gets it. Okay, so keep going for a few minutes. Again, it'll be recorded. So, okay, so what I'm going to do now is I'm going to load this. The place to load it is in load map. We always call load map before we call any other functions. I need to make a global variable so that I can get at this data after it's loaded from my implementation of that find function, my query function. I'm going to make a global variable, and I'm going to make a vector of vectors, and each of those stores a street segment index. So I'm going to visualize this in a minute. I'm going to load that up. So basically my load map, first I have to load in the streets database API. So this call does that. And now I can ask questions of the streets database API. So I'm making basically a vector of integers. And I'm calling it, give it a nice name. It's a global variable, so you should have really good names for global variables. So I'm calling it intersection street segments. Street segments of my intersections. So the first dimension of the vector is basically per intersection. So for every single intersection, I can look up what data goes with it. So this is the data for intersection 0, this is the data for intersection 2. Each of those data items is not just one number, it's actually a whole vector as well. So for intersection 0, let's say there are 3 street segments, you would have a vector of length 3, and it would have the IDs of each of those street segments. Okay, for intersection 1, maybe there are 5 street segments intersecting it, so it's kind of a complicated intersection. It looks like that. Well, we'd have a vector of length 5, and it would have all of those IDs. So if this was 301, one of these would be 301, and so on. Okay, so once we've created this data, so it's kind of like a 2D array. Yeah, it's related to a 2D array. Okay, and let's see. So that's, I'm not going to do the breakout rooms now. Let's just take a look at this. So to load this, the code looks very similar to what you just wrote. We've just kind of moved it to load map. Okay, so to make it a bit easier, we're going to basically say, make me the whole first vector. This resize call says, make a vector with this many entries in it. So we just made the first vector, first dimension, and it has enough entries for all our intersections. And then we're going to loop through, and for every single intersection, we're basically going to do the same code we had before. We're going to get all the street segments of that intersection. We're going to put them in a little vector, okay? And we're going to store that in the appropriate entry in our intersection vector, okay? So this code is going to make that 2D data structure for us. It's a little more convenient for me to use resize in this case and kind of create the first dimension of the vector all at once rather than using pushback. You could do it all with pushback, but again, it's a little more inconvenient because this resize means all the data in the first dimension now exists, and I can just index it here. Okay, so once I've done that, I've loaded all this data. My find function gets really short. My find function can now basically just return the data. And basically every element in that first dimension is the answer for one intersection. So if you ask me about intersection number 300, so that's passed in here, I just return entry 300 from my data structure. And that is actually a little vector with all the right street segments. Okay? So it's really fast. It actually hasn't changed the computational complexity, but it's reduced in this case, but it's reduced the constant, so it'll be faster. If we run the performance test, we run our tests again, we'll now see we passed. Now I see somebody saying, but load map's slower. And yeah, load map is slower, but load map is only called once when your program starts, so we don't care as much about its speed. People don't care too much about how long, if it takes a second or two to start a program. They care more about how fast it is when they're interacting with it. So we give you several seconds for load map, which is a long time. Okay? So this is a standard technique in programs to try to, if you can make the interaction of the program faster by doing some pre-compute when you're loading the program up, that's usually a good trade-off, as long as the load times don't get too bad. So we give you several seconds for load map. Unless you do anything really inefficient, your load map should never be a CPU problem for you. Okay, thanks. I'm a few minutes over. I'll hang out on the line in case you have questions, but that's it for today.